Hello. Um, this video will describe the Euler method for solving differential equations. So this is just going to be one method for solving differential equations. It's kind of the quick and dirty one. There are more sophisticated ones, but this will suffice for simple calculations. So the plan is, first I will describe a differential equation and what it means to solve a differential equation. And then I will describe the Euler method and apply it to a few different examples. At the end of the file um, associated with this lecture, there are some homework questions for you to do, and pay careful attention to this, because really these methods that are outlined here are the main tools that you'll need for your final project. So really your final project is just to apply these ideas to a different system. Okay, so before we get into the coding, let's go through and talk about differential equations, what they are, and what it means to quote unquote solve them. Switch over to the whiteboard. Sorry, struggling with the, there we go. Okay, so a differential equation is any equation relating functions and derivatives of functions to each other. So I could have f dx equals, I'll just choose something really simple. Let's just say it's minus some constant times f, where f is a function of x. Okay, so this is pretty much the simplest differential equation almost that you could imagine. And what it means to solve a differential equation is to be able to turn this around and write down f of x equals something, something, something. Okay, we'll do it here in a minute, but that's what it would mean to be able to come up with an explicit formula for f of x. So you're saying what function of x has would satisfy this equation, this relationship involving derivatives and functions. In general, there are different kinds of differential equations. They're linear, nonlinear, first order, second order. For us, what we really want to pay attention to is the order of the differential equation. So the order equals the number, sorry, the highest order derivative. Erase that. So this equation here would be a first order. If you had an equation which looked like the second derivative on f equals, I don't know, f squared. Maybe I shouldn't do the squared. I'll do so you don't confuse the two. Powers of 2, f cubed. This would be a second order differential equation. DEQ, DEQ. Okay, So the reason why it's important to know the order of the differential equation is that typically, well, really, when you solve differential equations, you have to specify what are called boundary conditions. And in the equations I'm going to have you guys solve, they are going to be so-called initial value problems. So you're basically going to have to specify extra information at the beginning, at some point in time or at some position, and then all later positions or all later times, the function will be uniquely determined. So, um, so for first order differential equation, and we're going to talk about initial value problems. Whoa, sorry. We will need one initial condition. And for second order differential equations, we will need two initial conditions. Okay. Now, I'm going to go through some examples here, and I claim in physics class, we've seen both of these facts. So I'll show you how. Before that, let's come back to our original differential equation that I started with, which said df d. How about we'll do df dt, so we can think of it as a function of time instead of x. And say it's minus k times f. So this one is pretty simple. In fact, all the differential equations that I'm going to talk about in this lecture are simple enough that you really don't need to know any new tricks. You can more or less just use the things you know to solve them exactly. Later, when you take differential equations, though, you will learn about differential equations that are not so easy just to solve. You'll learn lots of little tricks, but ultimately, most differential equations do not have simple, expressible, closed form, nice solutions, and you have to use a computer, which is why we're going to learn how to do that later. Okay. So to solve this, what I'm going to do is basically rearrange this and pretend that differentials are fractions. I'm going to write this as df over f and say that's minus k times t, sorry, dt. And then I'm going to integrate it on both sides. And I'm going to get log f equals minus k t up to some integrating constant. Okay. And if I turn that around, I basically can write down f equals e to the minus k t times some constant. So this plus c is equivalent to that constant. What is that constant? Well, as I've kind of suggestively labeled it, if you plug in time equals 0, so I should spell this out a little bit more. F naught would be e to the c. All right, so if you were to plug in time equals 0, the exponential just becomes 1, And this extra number that you have to specify, which is equal to the integration constant, is nothing other than the initial conditions for the function f. So at time 0, you have to specify a value. That's one extra piece of information. And then for all later times, it's determined. So f naught is an initial value for f of t when t equals 0. After you know that number or that value, the value of f of t is completely determined afterwards. Okay, and we only had to specify one value, f of 0 or f naught, because this was a first order differential equation. We'll see an example of a second order differential equation here in a bit. Okay. Let's do another example. Suppose we are told the following facts, which should be familiar to you if you've been in physics. Specifically, dv dt equals acceleration, and we'll take that to equal negative 9.81. Right? And suppose we want v as a function of t. Well, if you've had physics, you've already seen how to do this. You basically can do the same thing again. You can write this as dv equals minus 9.81 dt, integrate, and I get v equals minus 9.81 t plus a constant. This constant is nothing other than, so if you plug in time equals 0, this would go away. You see that the constant is nothing other than the initial value for v. So we learned that this constant is the same as v evaluated at time 0. So we learn that so if you specify that, then you have a unique function. So v of t equals whatever that initial constant is minus 9.81 times time. If you took physics from me, we've been calling this kinematic equation number 1. And it requires one initial condition, one extra bit of information to have a unique solution, because this was a first order differential equation. What if we wanted to solve for position? Then we would say dv dt, which equals acceleration, or we could say, and then we would also have dx dt equals v. So note, you could say that this is equivalent to saying that d2x dt is acceleration. Notice one second order differential equation is equal to two first order differential equations. That's one way to see that to solve a second order differential equation, you're going to have to specify two initial conditions. Excuse me. Okay, let's see how this will play out. So in this example, take a equal to negative 9.81. Well, we've already solved this top differential equation. So if we were to solve the second differential equation, we would solve for x as a function of t. So I can basically turn it around and say dx equals v initial plus, minus, sorry about this. dt, I could integrate it to find x equals v initial t minus 9.81 over 2 t squared plus c. That came from doing an integral on both sides. And that's what I get. And then this integration constant, that's nothing other than the initial value for x, called x naught. And so the final solution we get is that x as a function of time is x naught plus v initial t plus 1/2. And I'll go ahead and write it with a when a is constant. And the two initial conditions are x naught and v naught. And this is appropriate because the equations we're solving are equivalent to a second order differential equation. So it's a second order differential equation. So then you need two initial conditions. In physics 1, we've been calling this kinematic equation number 2. But from a math point of view, it's just another example of a differential equation. Okay, so that's kind of a lightning summary of what differential equations are and how you would solve them. Let's talk about how we will solve them numerically. Numerically, we've already seen that you can't really do calculus on a computer because of the discrete nature of representing numbers in a finite amount of memory. So instead, we have to approximately do calculus. So what we have to do is replace derivatives with some sort of a finite derivative. So we saw a forward difference derivative, and then we also had a backward derivative. We aren't going to use this one today, but I just want to remind you of its existence. if you could take a limit and really let x go to delta x go to 0, these two would be equivalent, but of course you can't on a computer. If you needed a second order derivative, you could just take del plus acting on del minus on f, although we won't have a need for that, because instead what we're going to do is not use this form. Instead, we're going to, when we have a second order derivative, we're going to write it as a combination of first order derivatives. I'll show you how that goes in a bit. So how do we solve, if we can't really do calculus, how do we solve a differential equation? The key, well, let's go back to our exponential example. Maybe that'll kind of get the idea. So we have an equation which says that the derivative with respect to time is minus k times f of x. And we're going to replace that with del plus on f this equation. Now, if we solve this equation, there's no calculus really here because there's no real derivative. You only get a derivative if you take the limit as delta t goes to 0. But we can't really do that. This is not a differential equation. This is really just an algebraic equation, although it may look very complicated. If we can solve that, then if we want to approximate the solution to the differential equation, we need to just make sure that the delta x is small. So we're going to choose a delta x, which is that is small, say, 0.001, or for example. Okay, some small delta x. And then that would ensure that this algebraic equation is pretty faithfully representing, sorry, I said delta x, it would be delta t, that this algebraic equation is faithfully reproducing the differential equation. And if the delta t you choose isn't small enough, you could always make it smaller and smaller and smaller and smaller. Or what we will do is actually study what happens as you take different delta t's, and you'll see how it just zeroes in on a good solution to the differential equation. So the way this would work is we write out this algebraic equation. So I write it out and I would get f of x plus delta t. Sorry, I keep saying x, it should be t because I'm taking a time derivative, minus f of t over delta t. That should equal minus some constant times f of t. All right, and then we're going to, so now what we're going to imagine is, assume f at time equals 0 is specified. Okay, so assume that that the initial value is determined. look what, and also delta t is given, say 0.001. Then my differential equation, which says f of t plus delta t minus f of t over delta t equals minus k times f of t. Okay, so if I apply this at t equals 0, this says f of delta t equals, well, that's going to be f initial minus k times f initial times delta t. This is all stuff that I know, right? So I am assuming that I know the initial value of f and I know delta t. So I'm assuming I know all these things. And so what I find is that knowing f of 0 immediately determines f of delta t. Okay, let's go again. So now if we know f of delta t is known, and remember, and delta t is known, then I can apply my I can apply this same formula again and rearrange it. I could say f of 2 delta t minus f of delta t all divided by delta t equals minus k f of delta t, which means that f of 2 delta t equals f of delta t minus k f of delta t times delta t. Okay, so we're assuming we're doing this process iteratively. So we initially knew f of 0 and delta t. We use that to find f of delta t. Let me write that slightly better way. So now at this iteration, this is a known, which means the right-hand side of the equation is determined, which means that the left-hand side is determined. So now we have f of initial determining f of delta t, which determines f of 2 delta t, which it turns out will then determine f of 3 delta t, and it goes on. And you can determine it for all future values. So you will have a sequence of values, f of 0, f of delta t, f of 2 delta t, f of 3 delta t, a whole list of values. And then that constitute, and as long as delta t is really small, then you're going to have a very close approximation for the values of the function. And so in this way, you have approximately solved the differential equation because you will have specified a list of values that the function could take. This is called the Euler method for solving differential equations. I'm going to rewrite it in a bit more. So schematically, the way this is going to play out is you're going to, let's have a function let's say more generally, we have some function. So let's do a first order derivative. And it's going to equal some function g. And actually, it could be a function of f or time. It could be pretty complicated. Although solving it by hand might be impossible, or hard at least. The computer doesn't really care about that because ultimately we're turning this into the calculus into algebra. When you replace the derivative with a forward difference derivative, this becomes f of t plus delta t minus f of t divided by delta t equals g, some arbitrary function of f and t. Turning it around, we have f of t plus delta t equals f of t plus delta t Now I'm going to write f of t, comma t, making it really explicit. Okay, so the idea is that on the right-hand side, so if you imagine that t is, say, the current value, the stuff that you know, you would imagine if you know this at the current value, it determines the function at a later value, which you can then iterate over and over and over to determine all the values. The way the Euler method will work in a computer is you would want to define delta t, and you have to think about what's going to come out of this. We're going to get a huge list of values out of this, f of 0, f of 1, f of whatever. Sorry, f of 0, f of delta t, f of 2 delta t, and so on. So we're going to have to define delta t. We're going to need to specify initial values. Some initial value. And for second order differential equations, you're going to have to do initial values. So maybe I should just call this initial values, and then it'll be okay. Okay, so you have to specify initial values. And then what we want to do is create a list or an array to store the different data points. So what I did was I created an array. Oh dear. I defined an array, and what I stored inside it were the points. So I initialized it at the very beginning as, say, time 0, so that'd just be 0, and f0. So this was just 0. All right. And then I created a loop And inside the loop, at each iteration, I basically went back to this, and I used the old values to define the new values. Something like this. I said, something like new equals old plus delta t times g of old. I don't mean gold. What I'm saying is the new value equals the old value plus delta t times g of the old values. And that works. And then we also have to change the time value. So this is updating the function f, and we also have to say that the new value of time and then you want to just do times 1 in that case, because for time you want to just add delta t. You don't want to multiply it by delta t. So you just say the old value plus and 1 time step, and that'll give you the new value. Finally, so you do that, and then this is all inside the loop. That's all fine. And then I said that points, well, basically, I just said append to, actually not append to, I think I did append, it doesn't really matter. So I said points equals append, and then I would say points here, I should write these as f new and f old, t old. There you go. So you're saying that the new value of f is the old value of f plus delta t times g acting on the old value of f. And the new time is the old time plus delta t. And then at each iteration of the loop, you would say that the new points, the points that you get, the new point, you just, at each iteration, you glue in the new information with all the accumulated old information. And at the end of the day, when you're done, so when the loop finishes, you have a list of time and function values, and you can reconstruct the graph of the function. So that's the Euler method in a nutshell. You turn calculus into algebraic equations, which approximate the calculus as long as the delta t's are small. And then you iteratively take the initial values to create the current values to create future values over and over and over. And then as far as programming it, you'd want to use a loop structure to just iteratively go through this process to generate these points one right after another. Okay, so that is how the Euler method works. Let's see how it plays out in the Mathematica notebook. Okay, so this is the Euler method for solving differential equations file. You'll have this in Blackboard. So here I have the same examples we talked about. Okay, so looking at this, you see that I have the differential equation. The first derivative of x with respect to time equals minus k times x. And we know that it has a solution. I think in the previous note I called it f, but it doesn't matter. You get an exponential type solution. What I want to do in this little section is kind of write a little bit of code that will approximately solve this using the Euler method, and then we'll plot the exact solution next to the algebraic solution. You'll see that they line right up. Okay, so I'm just the notebook just spells out what I did, writing things by hand. You replace the derivative with a finite difference, and then you can use the nth values to determine the next set of values, just like I described, and then we're going to place it in a loop. So here's an example with radioactive decay. I'm going to define a function g up here, and I'm going to say that the initial value for x is 100. All right, so here's g. G does not have the derivatives. Remember, g is the part without the derivatives. So g is the minus k times x, the right-hand side. G is going to be the right-hand side of the differential equation as I wrote it. Okay, so g is equal to minus k times x. I specified my initial values. I specified delta t, and k was just a constant. I'm going to choose a value just to work it out. And then I created an array, a list, which I initialized. So at the start, it just has the initial time and value of x, which is x naught specified above. And then I have a do loop, and I'm just going to go through this. I just said go through it 10,000 times. Doesn't really matter. We're just trying we're just trying to kind of show the method. Okay, so I went around, and at each iteration, I say that I update the array points, and I set it equal to, well, it would be the old values plus the updated values. So I want to include in my array this. So this is going to be, so if you think about it, at each iteration, so let's say j is 3. So we've done, so if when j is 3, you've already gone through j equals 1 and j equals 2. So what you want to do is, if you want to create the I'm sorry, you know the first value. So when j is equal to 3, you're actually constructing the third entry in your list of points. So is that right? I'm saying that backwards. When j is equal to 3, you're constructing the fourth value. That's right. So when j equals 3, you've already got 3 points stored in your array, data points stored in your array. So now we're working on the fourth value. So j equals 3 would refer to the previous value here, plus, so notice here in the first entry, I just added time. That's because I put time in the first slot, right? I've got a time and function. So I'm just saying, go to the jth value of time, the previous value of time, and then add delta t. And then go to the previous value of x, that'd be the second entry, and then add to it delta t times g evaluated at the previous, with the previous information. And you just iteratively do that over and over and over, and it reconstructs a sequence of points, and we can see how it goes. Right? By doing 10,000 points, they get so close together you can't even see that they're separate. So I'll do 10 points. Maybe that'll be, there you go. So you can see it actually constructs a sequence of separate points, but because I chose delta t to be so small, they are really close together. If I go back to my 10,000 number, it almost looks continuous to the human eye. Just for comparison, I plotted it next to the exact solution, which for this equation we actually know. And I don't know, if you really squint, you can start to see maybe a little bit of separation, but pretty much they're right on top of each other. Okay, it's hard to see the exact solution is supposed to be in blue, and the numerical approximate solution is supposed to be in red, and they pretty much just line right on top of each other. Okay. So that is how you can solve a differential equation. Let's do another one. And on this one, we're going to solve it, and then we're going to, yeah, that's right. So we're going to solve it, and you'll see that this works like you expect it to. All right. So this is going to be to solve kinematic equation 1. It's just the same example that we had before. So here's the answer, that V is supposed to be V initial plus AT. We're going to actually focus on this differential equation, though. F over m stands for force over mass. It just equals the acceleration from the previous slide. The right-hand side, the acceleration, is just going to be a constant. So for this problem, that right-hand side, we're just going to take g. It could have been a function of velocity and k, so we left it as a possibility, but in practice, or in actuality, for this example, we're taking this to be negative 9.81, just a constant. And then to solve this for v, we have to specify an initial value and an initial time. So here's our initial value, or I rewrote it all down here. G equals, here's my function g, here's the right-hand side of that differential equation. And then I specified my initial velocity, and I specified delta t. And again, I just took it to be some small number. And I'm going to go ahead and store the initial conditions into the array called points. And then at each iteration, I'm going to add to it, I'm going to basically update the previous value of time by 1, by delta t, I guess. And I'm going to update the previous value of the function f, or in this case, this would be the velocity. The function we're solving for is the velocity, with, I'm going to take the previous value plus delta t times g, whatever that was, which in this case is just going to be 9.81. And we do this over and over and over, and it's going to generate a solution. And you see so this is saying you throw something at 100 meters per second, which is really impressive because that's 200 miles an hour, and it takes so after 10,000 time steps, which would amount to about 10 seconds, the velocity has kind of started out large and positive and has decreased down. It's almost to zero after 10 seconds. And then you can plot that versus the exact solution, and you can see that it matches. Okay, so those are two examples using the Euler method to solve differential equations, and you get a feel for how it works. Now, second order differential equations. We're not actually going to use the formula for a second derivative directly. Instead, we're going to split the second order differential equation into two first order differential equations. Each of those can be solved like we did above. Okay, so here's a differential equation. Well, we aren't actually going to solve this one, but that's okay. Here's a differential equation given here, or more generally, let's just go to the general case, that I have the second derivative with respect to time is some general function of g. And we're going to come up with an intermediate quantity. Well, in this case, it actually has a physical interpretation. It's velocity, but we're going to come up with, just give a name to the first derivative of the function. And so our second order differential equation is going to become dx dt equals v, and dv dt equals g. And you can see that if you just take the output of this top equation and plug it into here, the second equation, you recover the original second order differential equation. So they're equivalent, but this just allows us to recycle our previous code. Okay, so the strategy now is the same, basically, except we don't have to update just time and our function. We have to update time, the derivative of our function, and the function. So we have to do 3 updates at each iteration in the loop. So what I did in my code is I defined something called capital G, which is going to handle all of the updates. And capital G, because it handles the updates for all the functions and time, is actually going to be an array, a list. So capital G, when you plug in the current values, it's going to give the right-hand side for the different functions. And the way I ordered this is I did time was the first slot, the first entry, V was the second entry, and X is the third entry. So I've kind of swapped the order of these two when I put them into my array for no particular reason. It's just what I did, so you understand what I'm doing. All right, so G has a 1 in the time slot. That's because the new value, well, you'll see. And then I have the original function G, which came from the differential equation, updates the velocity, and then I'm going to update position using velocity. Okay, so you're going to take a point Tn, Vn, Xn to find Tn plus 1, Vn plus 1, Xn plus 1. And the way we're going to do that is we're going to say that the new values are the old values plus delta T times this capital G function, right here. So look what that does. In the first slot, so it's going to add them. You're adding two arrays, it's going to add the elements. So it's going to say, for time, it's going to say t in the nth time plus delta t times 1. Well, that gives me the n plus 1 time. That just moves time forward one interval. And then for the velocity, the nth velocity, sorry, the new velocity is going to be the nth velocity plus delta t times what's in the second entry of g. That was the right thing, because I want to increase velocity by g times delta t. That's right. And finally, for x, I'm going to have the new value of x equals the old value of x plus delta t times the velocity evaluated at the old point. So that's how it's going to work. And then we just iterate it over and over and over and over and over to find the list of all points. Okay. So again, we already know the exact solution. There it is. I'm just rephrasing it, or I'm just reworking it now numerically. So F over m is acceleration from the previous, from when I worked it from the previously. To solve this, we have to specify two initial conditions because it has a second order derivative. So so there I am. F over m, the acceleration, there's my 9.8 number that I used before, and I'm going to specify an initial height and an initial velocity. So I'm imagining I'm throwing an object straight up in the air. So I just chose initial height of 1 meter, initial velocity of 10 meters per second. You can choose whatever you want. And then G has an argument, which was a list, and I called, when I defined G, I called it current values, because I'm using it the current values to find the future values. And for this problem, the first entry will be 1. That's always the case, because that's how you update time. The second entry is how you update velocity. That should be the right-hand side of the differential equation, which is what we call G, little g, up here above. So that's just going to be the negative 9.8 number, 9.81 number. And then to update position, we use the current value of velocity to determine the new value of position. Going back to up here, we're using the current value of velocity to determine the new value of position. And so I specified y equal initial is 1, v initial is 10. I specify a delta t. I specify points, and then I put it in a loop. So I specify the initial conditions in point of my data points, and I go through, and here I kind of try to find, just by tweaking it, how many iterations are needed so that you pretty much come back to or until you hit the ground. That's why I have this weird 2150 number. And I made a list. Now, it's a little trickier to make the list in this case, because I don't want a list of all the points. I just want a list of the positions. So what I actually did is made a list plot of a table, and inside the table, I didn't include, you'll notice it has for each value of I, it has entries 1 and 3. And so if you go back to the way I had my data points, look at here at points. The first entry, 1, refers to time, and the third entry refers to position. And so my table that I created did not have velocities. So it's just going to be a graph of time and velocities. If you wanted velocities, you could do that. Or we can modify it. We can do list plot of table and then because velocity for each data point, velocity is the second entry, so you could put that there. Basically what this is doing is reaching into your list of your solution and pulling out the pieces needed to reconstruct graphs of position and velocity now. Okay, so if we do that, and there you go, you get a graph of position and velocity. Notice when you're at the maximum height, the velocity is 0, as is reasonable if you've had physics. Now, you can do this, and I guess I claim without proving it to you, but it's true, that this will lie right on top of, it matches the exact solution. In general, your solution's only going to be good up to about order delta t. So you could always have an error of 0.01. You want to make delta t really small so that the errors are small. Now, for this problem, because we're talking about, because I solved it and I by hand figured out roughly when it was going to hit the ground. Rather than using a do loop, you could also solve the same problem with a while loop and just say run the loop until the height goes negative. So whenever the height is positive, you run the loop, and when it goes negative, you would stop it. So and you could do the same thing. All right. So you could solve the same problem and let the loop determine when the object actually hits the ground if you wanted to. Okay, so here is your homework. After watching this video and going through this file, it'll be available to you on the webpage. Add comments to the code, which solves the first order differential equation for radioactive decay. Go through, explain how the algorithm works, explain what are the inputs, how the data, how the solution is stored in the points array. Go through the loop, explain how the Euler method is working. Add lots of comments. The more comments you add on this, the easier it will make your life for question 2 and 3 for this problem, but for this homework, but also on the project. Then do the same thing for the differential equation for the trajectory of an object thrown into the air. Finally, modify the second order differential equation example, that would be this projectile motion problem, and include a drag force on the baseball, so on a baseball. So you're going to imagine throwing a baseball straight up in the air. Now, you don't really need to know any physics. I've given you the formula. So here's the original negative 9.81 that should be in your lowercase g function. And then you have to add to it this minus 1/4 1.2 times 1.2 times pi r squared times the absolute value of velocity times velocity divided by mass. Now, if you had physics, the 1/4 actually equals 1/2 times the drag coefficient, which itself is a half, so you get a half times a half, giving a fourth. 1.2 is the approximate density of air. Pi r squared is the area of a baseball. This handles the functional dependence of the drag force. It goes like a velocity squared, and the funny way of writing here is just to handle minus signs, and then you have to divide by the mass to convert forces into an acceleration. So I've given you the parameters for the mass, the radius of the ball, everything's in metric units, and so I've given you all the numbers here. So really, you need to go through and adjust the function capital G to account for the drag force. And what you'll see is it does slightly affect the trajectory of the ball. Okay, so that's your homework for this one. Good luck.